Alright, so this is the lab setup for the Spring Air Track lab. This region along here is the air track, and this box right here is the glider. We used a pull and clamp to vary the height of the air track, changing the angle here, and then use that height and the distance of the air track to calculate the angle to use in our calculations. We had to place a square piece of paper at the end of our glider to make it more visible to the motion sensor. We placed this motion sensor at the bottom of the air track so that we could track the position and velocity of the glider as it moved up and down the track. At the top of the air track, we placed a force sensor so that we could measure the force exerted by the spring as the glider went up and down the track. This position right here, XO, is the initial position of the spring from which we dropped the glider. This was when the spring was exerting no force, so it was only gravitational potential energy. And then the position X here that changed for each of our three trials was the distance from the spring equilibrium position that the glider traveled that we use in our calculations.
We solve for the spring constant K by using the equation for total mechanical energy and the spring force equation. Since an air track limits friction, we assumed in our experiment that the air track friction is negligible. There are no non-conservative forces. Therefore, the total mechanical energy is equal to 0 joules. At the beginning of the experiment, when the glider is at max height, there was no spring energy because the spring had not been stretched. There was no kinetic energy because the glider had not been moving, but there was gravitational potential energy because the glider was some distance above the ground. At the end of the experiment, when the glider had stopped moving, there was gravitational potential energy because the glider was some distance above the ground. There was spring energy because the spring had been stretched, but there was no kinetic energy because the glider had come to a halt. This gave us the equation mg max height is equal to mg equilibrium height plus 1/2 kx squared. We then proceeded to solve for k by subtracting mg equilibrium height from both sides of the equation. This gave us mg max height minus mg equilibrium height is equal to 1/2 kx squared. We then multiplied both sides of the equation by 2 and divided by x squared. This gave us the equation k is equal to 2 mg quantity h max minus equilibrium height, all over x squared. We plugged in the numbers and solved for the constant. Next, we used the spring force equation, F equals kx, to solve for the constant. We divided the distance from equilibrium by the force and solved for k. We plugged in the numbers and got the constant. We used this procedure for all three trials.
For our first trial, we had a low percent error because we chose a good starting angle. As a result of the square piece of paper we placed in front of the glider, we obtained accurate measurements for both our velocity and force graphs. We chose to use a square piece of paper so that the glider would move smoother and we could obtain more accurate measurements. We had to make sure that we placed the square piece of paper high enough on the glider so that it would not touch the air track. When we accidentally put the piece of paper too low, it created too much friction, and subsequently the glider did not move smoothly, as you can see. Our second trial yielded a large percent error due to the fact that we accidentally touched the glider once we had turned the air track on. This force added to the force in the negative y direction and caused the glider to move slower initially. In our third trial, we obtained a relatively large percent error due to the fact that we chose too small of an angle. This caused friction to take a bigger effect on the glider. Initially, we took a fourth trial, this one exhibiting our highest angle yet. However, as you can see, the angle was too high and the glider hit the front of the motion sensor. This happened because the air track makes friction almost negligible, so the force of gravity in the x direction was not strong enough to keep the glider away from the force sensor. We compared our three usable trials using their spring constant or k values. Overall, we found that a smaller angle would produce a higher k value. Although technically the k values should all be equal because we use the same spring, the lab error accounts for these differences. Because the air track makes friction negligible, energy should be completely transferred through an entire cycle. This means that only conservative forces are at work, so energy is conserved. The transfer of energy is shown through our calculations for total mechanical energy.